So yes, so I decided to make this a rather short break that we get faster to pizza and beer afterwards. Also that we get faster to lean. So I hope you had some time already to get to know some people and found some interesting topics to discuss. I already introduced Johannes. So he is at Amsterdam before, now, and he has been different universities, and now he'll tell us about lean. And let's see what we learn.
Yeah, thanks for the introduction, Tobias. So I will talk about lean. I do not work on lean itself. I use lean. I'm a lean user itself. So first I want to give a couple of slides introduction to lean. I want to talk about the future of lean 4. And then I also want to give a demo so that you get a little bit of the look and feel of lean, how it is to work with lean. So first to the lean theorem prover itself. The main developer is Leonardo Di Muro at Microsoft Research. A lot of people, I think, know him from working on the Z3 SMT solver. And a couple of years ago, he said SMT solvers have this huge problems that you do your work, you manage actually to prove a certain statement, and then you change something slightly in your model or in your statement, and it breaks down, and you don't know how to correct it. You need to adjust your heuristics again. And it's hard to do this kind of small changes. And actually, that's a nice thing with interactive theorem provers on the other side. It's not a push-button technique, but you need to invest a lot of time. But if you change something slightly, it's usually easy. Assuming that it's mathematically a small change, then it's still easy to adopt it. So one important thing in lean is it's dependent type theory. So similar to what you have in Coq or in Acta, and it's a very powerful functional programming language in some sense, where the types are so powerful that we can write down logic. I will tell you a little bit more about this. And Leo's original goal, he talked a lot to Jeremy Avigad, who is also into theorem proving, and he's at CMU. And the idea is to bridge this huge gap between interactive theorem provers, where you need to write down very detailed proofs sometimes. In Isabelle, you saw we had auto and so on. So in Isabelle, we have very nice, powerful tools, but still compared to SMT solver, Leo says there's much more possible. But on the other hand, as I said, automated theorem provers, you change something slightly, the logic is not very powerful. To sometimes state or to model something, you need to make shortcuts or something. So that's the main goal. I need to admit, I think it's not yet there. Lean is still developing. It's written in C++, which a lot of people in the theorem proving community do not like, because they like to work functional, and prefer to like Isabelle is written in ML. People are used to ML. It's very similar to HL, and C++ is something completely different. It's easy to introduce segmentation for or something like this. So. But there's a solution which is quite new in lean, and it's meta programming so that you can actually use the language you have in lean. As I said, the logic in itself is a functional programming language, and you can use this to write down your own tactics. I will show a little bit about this. And you can take a look at the lean prover website. There's a so lean, of course, is written in C++. You can compile it actually to JavaScript nowadays and execute it in the browser. So if you want to play around with it, you can either download VS Code, play around in VS Code, or just use the website. As I said, I'm personally a user of lean. I work on the MathLab, which is a mathematics library. And I think what's important to say is also that it's a classical mathematics library. A lot of people working with dependent types are working very constructively. But we said, okay, we assume the axiom of choice. So we are at the same level as set theory with axiom of choice. Actually, we are a little bit more powerful. Set theory plus cardinals, whatever, plus certain kind of cardinals, inaccessible cardinals. And then we have the usual stuff you would expect, actually. So we have I mean, when I say here we have lists, finite sets, and multisets, it doesn't only mean that we have like the definitions of it, but of course a lot of theorems around them. That's what you want always in a theorem proofer. The usual number hierarchy of natural numbers, integers, rational numbers, and then so of course the first three are all nicely computable. You can actually evaluate functions on them, and then the real numbers and the complex numbers you can only prove about them, and you can actually not execute them anymore. And there's stuff about linear algebra and so on. This is maintained by Mario Canario and me. Mario is a PhD student of Jeremy Avigad at CMU, and it's actually more and more lively in the last year or last half year. So we have now 21 contributors. At least that's what GitHub says. And we attracted actually now a couple of mathematicians. There's especially one mathematician, Gavin Parser, at the Imperial College in London. He's a number theorist, and he wants to, well, let's say, apply students to Lean now. Or yeah. So the idea is that there will be he will give a first year student course for the first or second year students in mathematicians, not computer science, mathematicians, and it will be a regular course, but in the exercises he will give them the opportunity to actually write down and Lean theorems and play around with Lean, so they can, so that he wants to figure out if it helps actually to expose students to Lean and see if it helps them to learn mathematics actually.
He should do like an experience report afterwards.
Sorry?
He should write down like an experience.
Yeah, I hope so. Yeah. I think that's really part of it. Yeah, and yeah, it's on GitHub and it's a sub-repository of the Lean proofer. Okay. As I said, Lean itself is a programming language, so it's a functional programming language. As I said, it has a very strong and powerful type system. It has a very nice type class system, which you can compare to in Java to interfaces, or in Rust to something like traits. And it has this kind of framework to synthesize terms, or constant words here, which are called tactics. I mean, you saw it already in Dimitri's talks that you call a tactic like auto or so on to synthesize proofs. But the interesting thing is that here in Lean, proofs are just terms of your language. So actually, these tactics can be used to synthesize your function in itself. And as I say, this kind of tactics can be written in Lean itself. Like a simple example, we want to define lists over a type alpha, arbitrary type of type, over arbitrary thing of type. You define it for the nil case, you define it for the cons case. And the same here, so yeah, you don't have quotes like in Isabelle, everything is normally written down. You can define notation. So we want to have like a notation for the empty list. We want to have a cons notation. You could also define square brackets where you enumerate a fixed number of list elements, for example. And we can, of course, define also functions like a map function. And here, alpha and beta are types. I don't need to annotate the types here because they can be inferred by Lean from the fact that I call list here with a type. You may wonder why there's a difference between curly braces and round braces. And the idea is that with curly braces, these are parameters which can be inferred from your arguments here, or from the return type, or from this argument. So the user does not need to write them down. The user writes down map f and the list. And the elaborator, so this the elaborator is the tool in Lean which actually, after the parsing phase, tries to figure out what's the type. It's like the type inference, but it does much more than just inferring type. It computes type class instances and so on. Yeah, and then we just write down equations we want to have to define our map. So we say for the empty list is mapped to the empty list, and if you have a cons, then we apply f to the first element. So that's the usual map function we see in most functional programming languages. One strange thing is that this map does not get the f applied to it. The idea is that these are like fixed parameters, and only the part here is changing. That's the only part we need to write down in our recursive call. You see it also here in list. So usually list is written with the type parameter, and here we don't write it down because it's a fixed parameter when we define it. It's just to so that we can also define something into the natural numbers. It's the same as map, so we do recursively on it. Okay, so I think this is a pretty much standard functional programming language, I would say. That's what most people know. But so now, how do you actually prove this lean? And the idea is that we use the Curry-Howard correspondence, which tells us that each logical proposition actually can be expressed or can be stated, is equivalent to a type, and then if this type is inhabited, if I can produce a term which has this type, this means actually that this inhabitance is a proof for the original proposition. As an example, when we have a implication P implies Q, this means that this is equivalent or corresponds to a function which gets a proof of P and produces a new proof for Q, for the statement Q. Or see, we have dependent function, which means this is again a function statement saying that you get the element X and you produce now a type P of X, where the result type actually depends on X. Imagine like you have something which gets a number and produces a vector of a certain length or something like this. And this is used to represent a for all quantifier. You can say, okay, P and Q is the same as can be represented as a product of, yeah?
So is the core logic of lean constructive?
The core logic is constructive.
Okay.
But we add, for example, in MATLAB, we just accept the X. We have something, a function which says choice. You give it a type, a proof that it's non-empty, and then it produces an arbitrary element. And that's, for example, choice. But the core logic itself, I will say a little bit more. So we care a little bit about computable functions, but mostly if you prove, especially, proofs are classic in our case. So there's a difference between, it looks the same, but actually there are slight small differences between actual proofs and definitions. And yeah, an interesting question is, okay, how do we define equality? And the simplest solution is, there are multiple solutions, but one is, for example, saying, it's Leibniz equality. So we say x equals y says that for all predicates or contexts around x, if p of x holds, then p of y needs to hold. And we can prove that this is actually what we expect from equality. That it's symmetric. We can prove that this is symmetric. We can prove that this is transitive, and that it holds for reflexivity. Is this clear? Or is this, yeah. So one thing is, what's important is that these are total functions. If we would accept functions which are non-terminating, we could prove false very easily. We just say, I have a proof of false. It goes from false to false. Or it just produces false and calls itself. This is obviously non-terminating, but it would be proof of false if we would accept non-terminating functions. So all functions need to be total. Of course, we can do a similar trick like in Isabelle, where we say, I want to do some recursive definition where I do not know if it terminates. And then I could use choice to prove law of excluded middle, which gives me a choice of, actually my function is terminating. Here's the actual value, or here's the number of steps I need to make, or it's not terminating and I return none or something. And one nice thing is that using the Curry-Howard correspondence gives us a very nice uniform language. So it says not only our terms, but also the types of our language are exactly the same language as our terms. Or especially also the proofs in our language are the same as our terms. But in Isabelle, these three are all separate languages. So how does it look like? For example, we want to define vectors. Vectors of a type alpha of length n. And here's really, that's why it's called dependent types, because the type depends on something which is not another type. So in Isabelle, you can define a vector alpha, but you cannot define a vector alpha of a length which is specified as a natural number. So we say, okay, vectors of length n are actually lists alpha, where we know that the length of L is equal to n. And this is now a proof. So we can see this as a, so this is just syntactic notation to write it down a little bit nice. It says subtypes list alpha, L length L is N. And this is actually, you can see it as a product of a value of this list L and a proof that this list L has a certain property, namely that its length is N. How do we do something with it? So one example is, for example, we want to define now a VMap, a map function on vectors. We do again like a recursive step or mapping or matching on it. So we analyze this element and it's just a product. So it's just a pair of a list and the proof that this list has length N. For the result, we say, okay, now create another pair. This is what these angle brackets are for. The actual list is map FL, and then we do a calculational style proof. This is just actually transitivity, but it's a nice way to write down proofs sometimes because it's very readable. You say, oh, actually the length map f of L is the same as length L, and here we have a proof to do. So I will do it afterwards, but then of course in Lean you need to do it before. And then we say, okay, the length of L is N, this is by H, so this is what we get here. And how do we prove length of map? Actually, so here we have our statement saying, oh, for our list length of map of FL is the same as length L. And now we do, as I said, we are in Carey-Howard correspondence, so we can do now inductive proofs which are actually recursive proofs or recursive function definitions. So we say, let's do a recursion on L. If it's empty, then we need to prove length of map f empty is length of empty. And the simplifier, we just have the simplifier, applies the usual rules on length and map and show it. So the simplifier will reduce both sides to 0 and you're finished in this case. And in the cons case, you say, okay, now apply again the definitional equalities we gave for length and map. And here do our recursive call. So we give the simplifier, we give him a couple of rewrite rules he should apply. Here's a standard basis, a database of rewrite rules. And here we call length map L again. And that finishes our proof. So that's how you write down proofs in Lean. And lemma essentially says also that you don't care what the exact result is. You care that there exists a proof, but you not care how the proofs look like. So Lean actually stores the proofs, but usually ignores it. For definition, of course, we care about the actual content. Okay? So, this was a short introduction to Lean itself. But now I want also, so currently we have Lean 3, but there will be hopefully in the next couple of months, there will be a huge change because Leo is currently working on Lean 4. And I'm very excited about this, so I hope it will be released soon. But these are some slides Leo gave at Galois in August. And I should he told me I can use the slides, but I should mention that this is all work in progress. So what we see now may change or is not even implemented yet, but it's just an idea. So, but I think it's a very interesting, some very interesting changes. So first the question is, what is the problems with Lean 3? So as I said, we can compile Lean programs, we can execute them, we can, for example, that's what we use for tactics. But the problem is that they are compiled to bytecode, and Leo wants to change them, actually compile them down to machine code to have a faster evaluation method. Another problem, which is a strange split, is that the Lean expression, as I said, most of the part is actually implemented in C++. But then they're on top of the kernel, for example, is a virtual machine, and you need to have like representation objects to represent expressions, which cost a lot of time and memory also. And for me, one big restriction is that, for example, the parser is very limited. The parser only allows certain parsing constructs. You can add new infix constants or simple binder notations or something specific for lists, for example, but that's all. And for example, as a user, I would like to be able to implement my own parsers like you can in Isabelle, for example. Also, elaboration strategies. The elaborator is the part of Lean which giving after the parsing you build up a syntax tree, but now you have a lot of holes you need to fill in, and that's what the elaborator does. And of course, different users have different needs for elaboration strategies, so it would be nice if you can change them, or can implement your own, or can provide your own to your users. And users cannot extend the equation compiler, which I will not mention here, but just. So Lean 4. It's developed by Leonardo. It's based on Lean 3, of course, but it will be, large parts will be rewritten. He and Sebastian Ulrich, who is a PhD student in Karlsruhe, and soon maybe Gabriel Ebner, who is a PhD student in Vienna. So they're currently working on it. And the idea now is to implement more of Lean in Lean. So currently it's just, mostly we can write tactics, but the idea is to write the parser, to have large parts of the elaborator, the equation compiler, which is like where you give equations and it produces then actually one Lean term. The code generator, so from a Lean term down to machine code, tactic framework again, and the outputs, this should be all implemented in Lean. So which is currently in C++, should be all implemented in Lean. Also, of course, there's an intermediate representation written in Lean. That's currently, I think, translated to C++, but Leo also wants to use, in the future, LLVM-IR. And only certain parts, very small parts, are still implemented in C++. Only parts which need to be very fast and or not depend on too much other things. That's, I guess, one of the reasons why I want to have the kernel, for example, written in C++. The idea of the kernel, of course, is that it's the only thing which we really want to trust. The kernel, when the kernel accepts a proof, then we want to trust this proof. So the question is, of course, do we trust it if it's written in C++? I think in theorem proving most people do not want to trust it. But the idea is that if we provide all this infrastructure around it, maybe users can implement their own kernel in Lean, for example, and have an efficient way to compile it down to C++ and have their own type checker and proof checker. Yeah, so how will it look like? So the idea is that you as a user interact with VS Code, it goes to the language driver protocol, and then you have this chain of, first you have the parser, which is, now the green parts are all implemented in Lean now. You have the parser, which builds up a syntax tree, and you elaborate it, adding like type class instances, adding also what we had in curly braces, what can be elaborated from your input types. Then it goes on to the elaborator is based on certain elaboration primitives which are still implemented in C++, but mostly it gives this information to the kernel, and the kernel is running on top of a certain runtime which manages all the objects. And it's important to have a specific special runtime, for example, to have expressions living in this, so that actually there's no difference if some object is defined in the kernel or it's actually defined in Lean. And that's what this part here is supposed to do. So the idea is that even the compiler from Lean terms down to the intermediate representation is implemented in Lean itself. Then for the parser, why do we want to have the parser in Lean, written in Lean itself? So the idea is that it should be very extensible, so that as a user you can actually implement your own domain-specific language. Let's say you want to have something very specific about certain, you want to have your own parser for your programming language, you want to do some software verification over, or similar. And the idea is that what you see here is actually just a chain of monads where you can add certain effects and so on, and the hope is that this gives you essentially error recovery, documentation, printing and so on for free in your parser. So that you just write down, for example, as a description of your language like this, and it's freely documented, and if some error happens and it needs to recover for the next command, that this all happens without you as a user need to think a lot about this. Then the parser produces syntax objects. Currently in Lean, these are just very special expressions. This is a little bit annoying because you don't get much information out of it, but here we have a nice representation in Lean itself. Then this produces kernel expressions of this type. It's a little bit much. I think Isabelle has like 6 different types to construct expressions. Yeah, here it gets a little bit more, unfortunately. But some are things like attach metadata to my expressions, which is often very helpful when computing with expressions. And then the idea is, of course, we want to have a compiler to go down to machine code. The idea is not only to implement in Lean so that it's easier to implement, but there are a lot of external contributors who want to actually verify something like this, to have like a more verified, in some sense, more verified, or more parts of your infrastructure are actually verified. But as we saw from Andreas' talks, this is a huge project, so I don't know if this ever comes or how much of this will be actually verified. So the compiler does code specialization and monomorphization. And what I think is interesting is that we can add arbitrary rules, which we need to prove, of course, but we can add proof rules and then add it to the compiler and tell the compiler applies this rule to optimize your code. So like what you do in GHC often, I think there's some pragmas where you can do it. Or what here, like map of map is the same as map over the compose function. Then we have that's the intermediate representation. We have the runtime itself is strict, so it's not lazy, it's strict. It's garbage collected and uses reference counting. I think a very basic runtime, what you have similar to what you have, I guess, in Python or maybe in Camera, I guess, I don't know. Okay, then maybe more like, that's why I think what you have. Yeah, and in Python you have more references. So.
Python, I think so.
Yeah. Okay, so and there are some compiler hints you can implement also. I think this is very nice to. What you often want to have is pointer equality. So you want to prove that, for example, two expressions are alpha equivalent, so equivalent modulo renaming. And as a fast path, you want to check first: are my two terms actually pointing to the same value? And to do this in the logic is really hard because your logic doesn't know about pointers, so you cannot. The compiler would optimize it, but there's no guarantee that the equality actually compares both elements. But what you can do, you can actually encode this in your function signature when you can prove. So you can say, oh, I have a function C which returns true at least when both elements are equal. What it does when both are not equal, I don't know. It could still return true, for example, if they're alpha equivalent, or it could return false. This is just identity in this case, but when the compiler generates code, it can directly compare the references, for example. Structured trace measures will be nice. And then he wants also to have better support for reflection, which means you produce a decision, you define a decision procedure and prove it's correct, and then you can actually use this decision procedure to prove something by saying, oh, by the way, I proved that when a certain formula which is interpreted by this denote function, this is assuming that my decision procedure returns true, then I can prove this, and now the kernel can actually have a more powerful, faster way to evaluate this decision procedure. That's what we often do in Isabelle, for example. It's compiled down to SML code and executed. In Coq, they have also a special interpretation mode for this kind of stuff, and of course we want to also have this in Lean. Okay. This was the first two parts, and now I want to show yeah, sorry.
It seems like Lean 4 is mostly about changing the tool itself, not all that much about changing the source language that I would use. So is the expectation that most of the Lean code in the wild?
That's my hope, yeah. Yeah. So there will be surely some changes, but my hope is that the changes are relatively small. It's not clear yet. I mean, Leo, I should also say that the Lean 4 is not developed in the open. So there's no GitHub repository where you can look at the sources, unfortunately. But Leo, I was talking in Oxford at Flock with him, and he said, yeah, there are certain smaller changes, but up to now it doesn't look to be too big. But Leo explicitly says there's no backwards compatibility from Lean 4 to Lean 3. So it could be that we need to rewrite our complete math lab again when Lean 4 comes out. We'll see.
And the expectation is that it's going to be open source eventually.
Yeah, it will be open source. But Leo, I think the thing was that for Lean 2 and Lean 3, there was always a lot of discussion how to do certain things. People wanted to have a mode for homotopy type theory, a more constructive way, or some other things implemented. And at some point, Leo said, "No, I want to have a quiet development. I want to do my stuff." And then, yeah. So, but he gives sometimes talks and says what he wants to implement. So that's what I know. Sorry?
Do you know when you can expect it
No.
to be released?
I have no idea. But I mean, this presentation was already much more detailed than the last presentation he gave in Oxford. So I didn't ask him yet if there's any release date. I think he will say when it's finished and it's released. Okay. Any further questions to this? Okay. Let me just. My idea is also to give a small demo, but I have a much simpler applications than Dimitri. The idea is just to write down a very simple function which finds the smallest element in the list. So given a element in the list, I return either the smallest element in the list or if the other element we passed in is smaller, then we return this one. Again, the idea is to make case distinction. So we say, okay, we have A. If we have the empty list, we return we return A. Or if we have a constructor, then we return find smaller and actually pass in here the minimum element. A, B, L. And then we want to do, of course, we want to prove the correctness of this function. And for example, we want to prove that now this element is either in A or in L. So we say it's in the list A concatenated L. How do we do this? Well, again, we make case distinctions. So the first element is the list. Then we have the A. And now here we need to provide a proof. And my hope is that this works by simplification. And we need to tell, so just as an explanation here a little bit, you see here our current tactic state, because with by we started to fill in some tactics. And here we see more error messages down here, but we can ignore them, luckily. And now what we need to add is actually unfold smaller, so everything is fine here. And Lean tells me, oh, you're just not finished, you need to do the const case. This const case is unfortunately a little bit more involved. So what we see here, now of course we need to show that find smaller A const B of L is in this list. Now we can show, actually this is just this part, and in Lean now we can also write a little bit more of more explicit proofs where we say like either proofs and Isabelle where we state explicitly what we want to prove. And the nice thing is Lean allows us to apply definitional unfolding in this case. So we can say instead of this part here, we can say, actually that's nothing else than find smaller min A B L. So we show find smaller min A B L is in A B L. And from this, that's what we have now. And well, one thing is, of course, we know our induction allows us to say for a list. Of course, so that induction works, this list needs to be this list actually. But here A is arbitrary, so we can say, okay, we now have from our induction rules that smaller min A B L is in min A B L, and this is from find smaller mem L, and here we can just write underscore, and Lean will actually compute, the elaborator will find out that this is nothing else than min A B. Now we have this. Now element says, okay, either this element is equal to the left side, or it's again an element in L. And we want to do a case distinction on this. And to do case distinction in Lean, we can use a match operator, which is the usual match operator we have just on elements. So let's write match. This, so the name of the previous, we can either give here a specific name, like induction hypothesis. If we don't give a name, it's just called this. So we match now this induction hypothesis with two things. Actually, hidden here in this element of insert is actually what we see here. There are two cases. One is or the left case or the right case. So or in left, for example. And here we see that actually what we get now is this, oops. Sorry. Let's call it H. H tells us that find small m A, B is L. That's what we get from our induction hypothesis in the left case. And now we want to eliminate this equality. And the thing is that equality in Lean is actually an inductive data type which only has one constructor. And when we say, oh, match on this constructor, it will actually eliminate this equality and replace everywhere this part with that one. But this only works if this is a variable, so we need to do a little bit of work. So we copy this part here, and we add this to our match statement. So now we say, we have an X, and it's replaced also here, what's important. And we can match on it, so it's reflexivity, and suddenly don't get any H anymore, but we get the minimum of AB is elemented in this part. And then we can use a simplifier to, let's say begin. And so the simplifier can also unwrite our logical parts, and now we need to prove that AB equals A or AB equals B. For this we can actually unfold min. Then we get here ifs and else, and we just say, I don't care, either it's A less B or B less A. We have split ifs versus which gives us two actually new goals, what we see here, two goals. And we can apply the simplifier to both by using this semicolon operator, for example. Otherwise, we say, okay, in the right case, we unfortunately here's something wrong with the syntax, so it's just like list.mem. When x is in L, it's the same as x element ABL. And this is again, we go into the right part here. So now we construct our proof and we say, okay, of this memory go to the right, and now we need to go to the right again. Oop. H, and we're finished with this proof. Now actually we can do a couple of more proofs. I decided let's copy some here just to have them finished. So now we proved that actually our find smaller finds, what we prove here is that when x is in L, that find smaller AL is an element which is less equal x. And what we prove up here is that find smaller AL is always less equal A.
Do you have there a binding issue? Because
sorry? So instead of dot we use comma, maybe?
No, I'm wondering why you... okay, yeah, makes sense. Forget it.
Okay, good. So, and what you use is, yeah. Then I just say, okay, now of course the problem is we want to find the smallest of a list, and we can only return an option type because we don't know what we return when the list is empty. And also remember that, as an important information maybe, that alpha can actually be the empty type. So we may not be even possible to construct a type, so we just say construct the elements, so we return none. And what we can do now also in Lean is define a main function and execute our program. So we can say, oh, we have main is just IO is just our IO monad. We read our arguments from our command line. We compute the smallest one of our arguments and print it. Let's do this. rerun it, and it's called demo.lean. I should save it. And let's say, I don't know, UC Berkeley, TU ETH, RVT, oops. And it compiles it, and it turns our available name is the one which is lexicographic, the smallest one. And we have a proof that this is correct. Okay. Okay, so this is my demo. There's nothing more I want to mention but this one. So Lean Forward is a new grant we got from the Dutch Science Foundation, I think it could be an English translation. It's about, again, formalization of mathematics in Lean, but there will be the Lean Together workshop for 4 days. And the idea is that everybody who is interested in Lean could join it. There will be talks about it, or there will be also tutorials working in Lean. So everybody who's interested is allowed to come and to join us. Okay, so that's all. Thanks for listening. Are there any questions? Or we
Let's
just
take like 1 or 2 short questions if there are some immediate. Otherwise, we have questions during.
Yeah.
So you showed these calculational style proofs.
Mm-hmm.
And the nice thing there is I can pretty much read that as a proof.
Yeah.
And then go back and I could write something similar by hand. But I mean, say for the proof you just developed in the demo, find it explainable?
So, let's say, I mean, the first 2 things for me are very nice to explain it, right? I say, now I need to, actually what I need to show, I restate what I show in this case again. So that's the first, this is line 13. I say, find smaller minimum of AB is in this set. And then I say, now I have this from induction, I get this fact, proved by this one line. Of course, this match statement here is maybe not as readable as anymore. But depending on how much you know about your logic, it can be actually readable because you have this you see exactly which cases you look at. You say, yeah, I know that I go into the left side of my OR, but I of course need to know that actually this memory state. What I have here. That this that this element blah 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 of cons is actually expressed as a logical OR, and I need to know that when I go to the left that I have an equality and I can eliminate this equality with a reflexivity. This is not any readable anymore, but the thing is that you get explicitly the structure, and as when you write down the proof, it's often very important that you have a lot of flexibility to write down your case distinctions you have. Also, I need to admit that in Isabelle, I think all this would be just by auto, mostly. And my hope is that in Lean we get this down to by auto in a couple of months also. With Lean 4 maybe, when we have faster evaluation methods. But for me at least, what I need to say is that when I have this standard, like here, where I say, oh, you do recursion over the construction of L. I think for me this is very readable, and that's how you write functional programs. When you're a functional programmer, this is like the basics for you. And of course here it's a little bit more integrated. You need to know more about your system but essentially the important thing is also that all the informations are written down actually. And if you just write down auto or some very strange tactic calls like simp, split if, simp, then you cannot read anymore a lot. But I write it down like this because I know that at some point the split ifs will be part of the simplifiers. It's a simplifier. If it sees a if statement, generates 2 new subgoals where the condition is true and the other one where the condition is false, and then continuous simplification. What Isabelle simplifier does. So that's why I would write it down like this. And of course, I often prefer proofs like this where you have really like, we need to show this, we do that, and then we continue like this, transitivity. I also wanted to show very shortly, sorry, something like sledgehammer, not really sledgehammer, it's much simpler. You can write down holes, like curly braces, exclamation marks, And then you get here a couple of things you can do with this, and one is to call tidy. Tidy is tries a couple of tactics and does a little bit more, and figures out if it goes, and then it replaces your whole by, in this case, for example, by a tactic call. And of course, in the future, we want to have integration of sledgehammers, and you write down calibrates exclamation mark, select sledgehammer. It runs for a while, and at some point, it gets replaced by a new proof. That's the hope. Yeah. Okay.
Cool. Very nice, I guess. I think we should close that because then we have a little bit more discussions. And yeah, well, thanks a lot for all the speakers. Yeah.